bring is not yet, but we will talk about those issues as well. Okay, let me know what you think about this one. Just I keep silent. So what do you think? Do we need robots to really have the perfect appearance of a human? Or like we need the functionalities of the environment? Like if we are working with the trees, we specialize the robot to cut trees. If we are working in the human environment, then we will have a robot that has the functionalities of 2 arms, the mobility, the vision capabilities. So these are really interesting issues to think about, whether we need to have the robot biologically based or functionally based, and how we can create those interactions in an effective way. Last one I think is, yeah, this is an interesting example of how we can extend the capabilities of human with an exoskeleton system. So you wear it and you become a Superman or a Superwoman, and you can carry heavy loads. They will demonstrate here carrying, I believe, 60 kilograms without feeling any weight, because everything is taken by the structure of the exoskeletal system you are wearing. Another interesting one is this one from Tokyo Institute of Technology, a swimming robot. So make sure no water gets into the motors. Anyway, the thing is, robotics is getting closer and closer to the human, and as we see robots getting closer to the human, we are facing a lot of challenges in really making these machines work in the unstructured, messy environment of the human. When we were working with robots in structured manufacturing plants, the problems were much simpler. Now you need to deal with many issues, including the fact that you need safety. You need safety to create that interaction, and this distance between the human and the robot is very well justified. You don't want yet to bring the robot very close to the human, because these machines are not yet quite safe. Well, the development in robotics has many aspects and many forms, and really at Stanford we are fortunate to have a large number of courses offered in different areas of robotics, graphics, and computational geometry, haptics, and all of these things. And you have a list of the different courses offered all along the year. And in fact, in my this is the Intro to Robotics. In spring I will be offering 2 additional courses that would deal with experimental robotics, that is applying everything you have learned during this class to a real robot and experimenting with the robot, as well as exploring advanced topics in research, and this is in advanced robotics. So you realize I'm Usama Khatib, your instructor, and you have this year, we are lucky, we have 3 TAs helping with the class: Pete, Christina, and Shanning. So let's, they are over here. Please stand up, or just turn your faces so they will recognize you. And the office hours are listed, so we will have office hours for me on Monday, on Wednesday, and Monday, Tuesday, and Thursday for the TAs. The lecture notes are here, and they are available at the bookstore. This is the 2008 edition, so we keep improving it. It's not yet a textbook, but it is quite complete in terms of the requirement and the things you need to have for the class. So let's see. The schedule, so we are today on Wednesday the 9th, and we will go to the final examination on March the 21st. There are few changes in this schedule from the handout you have, and we will update these later. There is these changes happen just in this area here around the dynamics and control schedule. But essentially what we're going to do starting next week is to start covering the models. So we will start with the spatial descriptions, we go to the forward kinematics, and we will do the Jacobian, and I will discuss these little by little. That will take us to the midterm. One important thing about the midterm and the final is that we will have review sessions. And the class is quite large, so we will split the class in two, and we will have two groups that will attend these review sessions, which will take place in the evening. And they will take place in the lab, in the robotics lab. And during those sessions, we will cover the midterm of past years and the finals of past years. And what is nice about those sessions is that you will have a chance to see some demonstrations of robots, and at the same while eating pizza and drinking some. So that will happen between 7 and 9. Sometimes it goes to 10 because we have a lot of questions and discussions. But these sessions are really, really important, and I encourage you, and I encourage also the remote students to be present for the sessions. They are very, very helpful in preparing you for the midterm and the final. So as I said, this class covers mathematical models that are essential. I know some of you might not really like, well, getting too much into the details of mathematical models, but we are going to really have to do it if we are going to try to control these machines or build these machines, design these machines. We need to understand the mathematical models, the foundations in kinematics and dynamics. And we will then use these models to create controllers, and we are going to control motions, so we need to plan these motions. We need to plan motions that are safe, and we need to generate trajectories that are smooth. So these are the issues that we need to address in the planning and control, in addition to the fact that we need to touch, feel, interact with the world. So we need to create compliant motions which rely on force control. So force control is critical in creating those interactions, and we will see how we can control the robot to move in free space or in contact space as the robot is interacting with the world. And then we will have some time to discuss some advanced topics, just introduce those advanced topics so that those of you who are interested in pursuing research in robotics could make maybe plans to take the more advanced courses that will be offered in spring. So let's go back to the problem I talked about in the beginning, the problem of moving this robot from one location to another. Suppose you would like to move this platform. This is a mobile manipulator platform. You would like to move it from here to here. How do we do that? Well, we said essentially what we need to do is somehow find a way of discovering a configuration through which the robot reaches that final goal position. And this is one of them. You can imagine the robot is going to move to that configuration. But the problem with this is the fact that if you have redundancy, so what is redundancy? Redundancy is the fact that you can reach that position with many different configurations because you have more degrees of freedom in the system. And when you have redundancy, this problem of inverse kinematics becomes really difficult problem. So, but if you solve it, then you will be able to say, I would like to move each of those joints from this current position, this joint position, to this joint position. So you can control the robot by controlling its joint positions and by creating trajectories for the joints to move, and then you will be able to reach that goal position. Well, this is not the most natural way of controlling robots, and we will see that there will be different ways of approaching the problem that are much more natural. So to control the robot, first you need to find all these position and orientation of the mechanism itself. And that requires us to find descriptions of position and orientation of object in space. Then we need to deal with the transformation between frames attached to these different objects. Because here, to know where this end effector is, you need to know how, if you know this position of those different objects, how you transform that descriptions to find finally the position of your end effector. So you need transformations between different frames attached to those objects. So the mechanism that is the arm in this case is defined by a rigid object that is fixed, which is the base, and another rigid object that is moving, which we call the end effector. And between these two objects, you have all the links that are going to carry the end effector to move it to some location. And the question is, how can we describe this mechanism? So we will see that we are using joints of different kinds, joints that are revolute, prismatic, and through those descriptions we can describe the link, and then we can describe the chain of links connected through set of parameters. Don't worry, Denevitt and Hartenberg were two PhD students here at Stanford in the early 70s, and they thought about this problem, and they came up with a set of parameters, minimal set of parameters, to represent the relationship between two successive links on a chain. And their notation now is basically used everywhere in robotics. And through this notation and those parameters, we will be able to come up with a description of the forward kinematics. The forward kinematics is the relationship between these joint angles and the position of the end effector. So through forward kinematics, you can compute where the end effector position and orientation is. So these parameters are describing the common normal distance between two axes of rotation, and so this distance, and also the orientation between these axes. And through this we can go through the chain and then attach frames to the different joints, and then find the transformation between the joints in order to find the relationship between the base frame and the end effector frame. So once we have those transformations, then we can compute the total transformation. So we have local transformation between successive frames, and we can find the local transformation. Now, once we know the geometry, that is, we know where the end effector is, where each link is with respect to the others, then we can use this information to come up with a description of the second important characteristic in kinematics, and this is the velocities. How fast things are moving with respect to each other. And we need to consider two things, not only the linear velocity of the end effector, but also the angular velocity at its rotate. And we will examine the different velocities, linear velocities, angular velocities, with which we will see duality with the relationships between torques applied at the joints and forces resulting at the end effector. Forces, this is the linear forces are associated with linear motion, moment torques associated with angular motion. And there is a duality that brings this Jacobian, the model that relates velocities, to be playing two roles. One, to find the relationships between joint velocities with end effector velocities, and one, to find the relationship between forces applied to the environment and torque applied to the motors. The Jacobian plays a very, very important role, and we will spend some time discussing the Jacobian and finding ways of obtaining the Jacobian. So the Jacobian, as I said, describes this v vector, the linear velocity, and the omega vector, the angular velocity, and it relates those velocities to the joint velocities